Hello, so if you remember in the last few videos we've been looking through these things called probability distributions and basically all a probability distribution is it's a way of linking outcomes with the associated probability of that outcome occurring. And we started off by looking at things like rolling dice. So if you roll a dice, the only outcomes you can have are like 1, 2, 3, 4, 5 and 6, and you can find the associated probability. So the theoretical probability should be 1/6, and then we said, well, okay, in that case all the outcomes are equally likely and we get ourselves a uniform distribution. So by looking at certain characteristics of our random variable, we are able to come up with certain types of distributions to describe that. And we also looked at binomial and Poisson. So these were all types of discrete distributions. In other words, where the outcomes can only be set values within a given range, okay? Now in the last video we started looking at the normal distribution, and we basically saw that the normal distribution is really just the limiting case as you consider more outcomes of the binomial and the Poisson distribution, okay? And we kind of looked at that in quite a lot of detail with the balls dropping down through the Galton board into the set bins. We basically said, well look, if we take away the bins, in other words it's no longer discrete, the ball can land anywhere it likes, you can have any outcome, then you get yourself a continuous random variable, and the classic continuous random variable is the normal distribution. So we're going to continue playing on that idea today. But before we get there, I actually want to take you back to something that we've already looked at. If you remember in the first ever video we did of representing data, I gave you this slide and I said this really underpins the very thing, the very fundamentals of what statistics is all about. And I'll just go through it again because it's a really important idea and it's a really important analogy to think about. So effectively, we've got ourselves a cake, and it's a really big cake. It looks really, really delicious, but we want to ask ourselves the question, is this cake delicious? Is this cake yummy? Does it taste nice? Now, clearly, we do not need to eat the entire cake in order to understand, in order to answer that question, okay? Because what we can do instead is we can just take a little slice of cake and eat that little slice of cake. And the idea is if that slice of cake tastes nice, then we can understand what is happening with the rest of the cake. So in other words, if the slice of the cake tastes nice, we can then understand whether the big cake tastes nice, the whole cake tastes nice or not. So what we've effectively got going on here is a population. So our big cake is our population. It's the entire group which we're interested in. In this case, it's the entire cake. And then this little slice of cake that we've got going on over here is our sample. Okay, and we've talked quite a lot about sampling. This really is the very fundamental kind of idea that underpins all of statistics. It's the idea that you don't always need to look at the entire population. Sometimes you can just take a sample, and if you understand how that sample relates to that population, in other words, you can make an inference about the population from the sample, then that's enough, okay? And this really is where we're going with all of this kind of, all the things that we're looking at the moment, okay? And if you remember, there's two really key terms. If you're looking at a measurement of a population, then you're looking at a parameter, okay? So a measurement of a population, such as average weight or standard deviation or something like that, that's all talking about parameters. So a measurement or a characteristic of the population, we call that a parameter. Whereas a characteristic or a measurement of the sample, we call that a statistic. So for example, the average weight or the average height or the standard deviation of the sample, we call that a statistic. So just remember, if you're working with a measurement of the population, we call that a parameter. If you're working with a measurement of the sample, we call that a statistic, okay? And the idea is that you want to understand how taking samples can infer information about the population, because clearly samples are better for it's easier to take a sample, and it's also easier to process data from a sample, whereas a population, for example, if you look at everybody in the entire world, every human in the world, I think there's like 7.8 billion people in the world, that's going to take a lot in terms of analysing and also collecting that data. Okay, it is possible through censuses and things like that, but it's going to take a lot of work. Where does data fit into all of this? Well, if you like, the data are the raw ingredients. It's the thing which makes up either the population or the sample. So it could be like loads of heights or loads of weights, things like that. Okay, so the data is kind of the raw ingredients. It's the thing which makes up the entire population or the entire sample. Okay. So what we're going to play on today is really kind of the idea of how a sample can infer something about a population. So in many ways, this video here, which we're going to call the central limit theorem, which we'll get to later, this really kind of underpins the very idea of statistics. It's all about understanding how sample level data tells you things about what's happening at the population. Okay, so it's about how we make that inference. This is what it's all about. Now, I'm going to start with an example, okay? So I've got here song lyrics, and these are song lyrics from the song Crazy in Love by Beyonce. Now, let's suppose that we want to work out what the average word length, or the mean word length, let's call it average mean, what the mean word length of Crazy in Love by Beyonce is. So I've got all the lyrics here, okay? So yes, it's so crazy right now, most incredibly, etc, etc, etc. And I want to work out the average word length. In this case, the average is the mean, okay? So what's the mean word length? Well, are you happy? There's a couple of different strategies that I can use here, okay? The first strategy is just simply count the number of letters in every single word. So I just bring up every single word and I say, okay, first word, 3 letters. Next word, 3 letters. Next word, 2 letters. Next word, 5 letters, etc, etc, etc. Count the number of letters in every single word and then take the mean of that. Now, what I'm effectively doing there is a census because I'm looking at the entire population. Are you happy that the entire population is every single word, so the entire song, okay? Now, the thing is, this is going to be very accurate because I'm working with the entire population. So therefore, whatever average I get, that would be a parameter. In other words, it would be the true mean word length of the entire song. However, it's going to take a long time to do, isn't it? It's going to be fairly impractical to do. I mean, you just think I've got to go through every single one of these words, and I don't know how many words there are in the song, but I'd imagine there's something like 200-300 words there, and I've got to go through, count the number of letters in every single word, write those numbers down, and at the end I've actually got to physically stick all those numbers in my calculator and take the average of them. Now that's going to just take forever, okay? So it's going to take a long time, it's impractical, but I'm aware it will be more accurate. So what I want to do is come up with an alternative strategy then, and this is where our idea of a sample comes in. Just remember, a sample means you don't need to take the entire word, take the entire song, sorry, you don't need to look at the entire population. You can just take a selection, you can just take a subset of words. Find that, so say for example 5 words, find the number of letters in each of those 5 words, take the average of that sample. Now, the thing is, if you do this, it's going to be less accurate, okay? You've also got to make sure it's random, and we've talked about different methods of sampling, such as like stratified sampling, etc., in the first video. So it's going to be less accurate. You've got to make sure it's random. However, it's quicker and easier to do. So in all honesty, you know, these two strategies, we tend to just take a sample, but just be aware it's going to be less accurate. So quicker, easier, yes, but less accurate. Whereas if you do the entire song, yes, it's going to take a long time and it's going to be more impractical to do in some cases, but it's going to be more accurate. So just be aware of the advantages and disadvantages of both strategies. But of course, the whole idea of this video is I want to understand how looking at sample level data will tell you something about the entire population. Okay, so I'm going to look at strategy 2 and see how I can make that inference more accurate. Okay. So what I'm literally going to do here is I'm just going to bring up the song. I'm going to take 5 words at random, going to count the number of letters in each word, and I'm going to take the mean average of the number of letters. So here are my song lyrics, and I'm just going to go through and just randomly select 5 words. Now, of course, it's up to you what you mean by random here. I mean, I'm aware that I'm not using any kind of random strategy other than I just go, right, that one, that one, that one, and that one. But of course, then you can kind of say, well, actually, humans aren't that good at being random. So I could use better analysis or better methods to be random, but actually, to be honest with you, in this case, to get the message across, I'm just going to select 5 words from the song, okay? So I'm going to select most, more, looking, not, and got. So here are my 5 words, and I'm just going to count the number of letters in these 5 words. So most has got 4 letters, more has got 4 letters, looking has got 7 letters, not has got 3 letters, and got has got 3. So these are basically my my sample data. So 4, 4, 7, 3, and 3. These are the number of letters in each word of my sample. So now what I need to do is take the mean average. So if I look at 4, 4, 7, 3 and 3, add them all together, divide by the number of things in my sample, in this case 5, I find that the mean number of letters is 4.2 for this particular sample, okay? So the thing is, I need to look at this and say, how can I improve the accuracy? Because I basically said with this strategy, yes, it's very quick and easy to do. Like I could literally do that in a couple of minutes, okay, if that. And I find that the average word length for my sample is 4.2. But then how can I make this more accurate? Because I'm pretty much certain that the average word length of the entire song is not 4.2. I'd hope it's going to be close to 4.2, but it's probably not going to be exactly 4.2. It's highly unlikely that's going to be the case. So I want to improve the accuracy of my sample. So the way in which I could do that is just simply by doing this over and over again. So take 5 more words, and then another 5 words, and then another 5 words. And each time I'm calculating the mean average of the number of letters in my sample, okay? So I'm not going to do that by hand. What I'm going to do instead is actually get a computer to do it. So I've written a bit of code. I use R, which is a statistical package, which allows me to basically import all of the words from these lyrics, and then effectively I can just basically write a bit of code, and it will basically do exactly what I've just done by hand on the previous slides. Just take 5 words, count the number of letters, and then take the average number of letters. And it just does that. I just do that over and over and over again. So every single time I take 5 words, then take the mean average of that sample. Now, if you are interested in this code, I have actually linked it on the VLE, so you're more than welcome to go away and actually have a look at that code, download R and actually try running your code yourself, and perhaps you might want to do that with different songs. If you just put your song lyrics in a text file and import that text file, then that will work quite nicely, okay? But basically, if I get my computer to do, let's say, 1,000 samples, then basically I get an output that looks like this. So the first sample that it collected, so each number represents a sample of 5 words, and then it's taken the mean number of letters in that sample of 5 words. So this first number, which is 3.4, basically represents that there's 3.4 as the mean number of letters in the first sample of 5 words. Then the next number, which is 4.6, is going to basically say in the second sample, select 5 words, is the average number of letters, or the mean average number of letters, is 4.6, and so on. So the third sample, the mean average is 4.2 number of letters, and 3.6, and so on. So basically each number represents a sample of 5 words where I've just taken the average of that particular sample, and I've just done that 1,000 times in my computer. So then what I can do is basically look at this, look at all these numbers, and take the average of all of these numbers. And again, I've done that in a computer, okay? But effectively just add together all of these numbers, divide by the 1,000 samples that I've got, and I basically find that the average of those averages is 3.5. Okay, so that's one way that I can get a better approximation of what the true mean word length of my population is, of my song. Okay, so I'm basically proposing it's about 3.5. Now, are you happy that that is different to the 4.2 that I took with one sample? So I'm more confident it's more accurate because I'm working with more data, okay? I'm doing this sampling method over and over again, and then basically taking the average of those averages, and I basically find out that the mean word length should be around 3.5. So I'm more confident with that 3.5 than I was with the 4.2 that I did with my first sample, okay? So basically what I'm going to do is I'm going to show you what happens as I take more samples. So if you want to actually have a go at this, please feel free to come to my GeoGebra links. This is something that I've created in GeoGebra, and the link is there at the bottom of the screen. But effectively, if I come to this GeoGebra link, I get something that looks like this. Now, just to kind of explain what's going on here, I've basically imported all of those 1,000 numbers. So you remember each number, which represents the mean average of my sample of 5 words, I've basically imported into this spreadsheet in GeoGebra, and you can see all these numbers down here. Okay, so each number, remember, just represents a different sample. So that's the mean average of my first sample, mean average number of letters of my second sample, mean average number of letters of my third sample, etc., etc., etc. Now what I'm going to do is I'm actually going to plot this on a histogram along the bottom, okay? So you can see, for example, I've just taken one sample, I've just taken my first sample at the moment, and you can see that my bar here, okay, my histogram, it's got a height of 1, because I'm basically saying I'm selecting one sample, and that sample is at 3.6. So you can see I've slotted it in here. And then what I can do is actually increase the number of samples. So if I want to consider 2 or 3 or 4 or 5 samples, I can basically increase the number of samples that I'm considering and then plot them on my histogram down here. So what I want you to notice is what happens as I increase the number of samples. That's 2 samples, 36 samples, 56, etc, etc, etc. So all I'm doing is just considering more and more samples. I'm just basically considering more and more of these average mean word lengths and plotting them on a histogram. So look what we get. We get this kind of shape of curve here. And you can see I've kind of drawn a curve over the top. Now, hopefully you recognize this. This should be the normal distribution, and that's totally to be expected. We've said that as you consider more and more samples, whether the original distribution was like binomial or Poisson, whatever it might be, okay, as you consider more and more samples, it will tend towards a normal distribution. So we totally expect it that the average word length should be somewhere in the middle, and then there's less probability, or there's less likelihood of obtaining a sample which is further away from the kind of main bulk of my data in here, okay? But what I want you to do is actually, I'm going to play that again. What I want you to do is notice what happens with this distribution as I consider more word samples. So can you see that this sample, this distribution, the shape of the curve, is effectively becoming more peaked? I think that's a good way of explaining it. So as I consider more and more samples with a few samples, okay, my curve is quite flat and quite spread out, okay? But then as I consider more and more samples, my curve is becoming more peaked. In other words, it's less spread out, okay? So if I actually make a sketch of that, okay, I'm basically saying that with a few samples, I get a curve that looks like this. So here's my curve with a few samples. So something that looks like that, okay? But then basically, as I consider more and more samples, my curve is becoming more peaked, okay? So basically, as I consider more samples, there's a couple of things which are happening. My curve is effectively becoming more peaked. So let's actually just explain what I mean by more peaked. Okay, so more peaked is kind of the informal language. Let's actually define really what I mean by more peaked. Well, are you happy it becomes centered around the same value? So actually the center of the distribution doesn't really change. So let's just see that again, okay? As I change the number of samples, okay, the center of the distribution remains relatively the same. Okay, so the distribution, the center doesn't really change. And actually, what should the center of the distribution be? Well, it should be what the true population mean should be. So what the true population mean word length is. And that kind of makes sense. You consider more and more samples, you consider more and more things in your sample. You're basically saying that whatever your sample mean is, okay, so whatever 3.6 or 4.4, as you consider more and more samples and you then take the mean of all of those, then effectively, X bar should approach the true population mean. In other words, this distribution should become more centered around the true population mean, okay? So that's the first thing I want you to notice. So as I consider more samples, so if I just say my sample size is n, the number of samples is n, and as I increase that, so I'm going to write it as n approaches infinity, because I just need to basically say n gets bigger. Well, big thing is infinity, right? So the first thing which I notice is that this kind of distribution becomes more centered around the true population mean. In other words, the sample mean, the mean of my samples, approaches what my true population mean value should be. So if you like, on this side, this is the mean of my samples. So in other words, it's a statistic, okay, because it's an average. And on this side, I've got my parameter because I'm looking at a population, okay? But you also notice that the shape of the distribution, okay, down here, it's really spread out. So with a few samples, it's really spread out. Then as I increase the number of samples, it becomes less spread out, okay? So the spread decreases. Well, what feature of a distribution describes my spread? Well, I can basically say the feature of my distribution which describes the spread is the standard deviation, okay? So the standard deviation, which I'm going to write as S because I'm looking at sample, that should effectively become smaller because the spread of my distribution should become smaller, okay? For like low number of samples, so like for n equals 5 or something, it's quite a spread out distribution. But then as I consider more and more samples, for example, like n equals 1,000, that distribution effectively becomes less spread out. So the spread is decreasing, okay? It's kind of becoming more pointed, okay? And the feature which describes the spread is the standard deviation, okay? But you also notice as well that if I look at a value out here, for example, so let's suppose this is some particular value. Let's suppose this is like x bar 2. Okay, what's the probability that I end up at some value out here? Well, if I only looking at like 5 samples, then I'm basically saying that probability is way up there. So remember, the height of the curve gives you your likelihood. It's the probability of getting that outcome. So it's quite a high probability. But if I look when I take more samples, that probability is effectively decreased, okay? I've gone from a probability up here, so quite a high probability, to a probability down here. Remember, the height of the curve just gives you the probability. So it should also be that if I'm looking for the probability of obtaining a sample away from the true population mean, so in other words, away from this kind of region here, well, if I'm only looking at a small number of samples, that probability should be higher, and then as I consider more and more samples, that probability effectively decreases. In other words, the probability of obtaining outliers, the probability of getting a sample which is an outlier, should decrease. Yes, there is still some probability that I will get an outlier, but that probability should decrease the more samples that I take, okay? So in other words, the probability of obtaining an outlier, the probability of obtaining a value which is further away from the true population mean should decrease, okay? So the probability of obtaining an outlier should decrease. Okay, so I can summarize this then in a really nice way. So I've just basically said, as the samples increase, the number of samples that I'm taking increases, and I can write that notation as n approaches infinity, number of samples gets large, then the mean of the samples approaches what the true population mean value should be. So the mean of the samples, which remember is x bar, should approach the true population mean parameter, which is mu. Okay. It's also the case that probabilities for other sample means decreases. So in other words, the probability of getting a value out here, as I consider more things in my sample, the probability of getting an outlier should decrease, okay? But it's also the case that the standard deviation of the sample should decrease as well. In other words, the curve is becoming more pointed as you consider more samples. So these last 2 points are really related to each other, okay? And this is really what the central limit theorem is telling you. It's literally how you infer a sample level data. So okay, I've got myself a sample statistic. Well, you need to consider how many things are in your sample. And the idea is that as you consider more samples, then it should be the case that the mean of the samples approach the true population mean. So you're more confident in your mean of your samples. And also the spread of the distribution decreases, which means that the probability for other sample means decreases. So the probability of getting outliers should effectively decrease, okay? So let's actually look at an example then. Now this example is not actually based on the central limit theorem just yet. The next example will be. But effectively you're saying that crunchy caramels, so let's say that we've got a type of sweet, we're going to call it crunchy caramels, and we know that these types of sweet are going to be normally distributed with a mean weight of 50 grams and a standard deviation of 3. So if I define my random variable, which is always good practice when you've got random variables going on, regardless of whether they're discrete or continuous, we're basically going to let the letter x represent the weights of our crunchy caramels. So x is the weight of crunchy caramels. And then I can write that because I know they're normally distributed, so x is normally distributed with a mean weight of 50, and remember the number that goes here, the parameter that goes here is the variance. So if the standard deviation is 3, the variance is 9, which I'm going to write as 3 squared. Okay, so I'm just setting up my problem here. Now, let's suppose that I walk into a shop and I choose a crunchy caramel at random. What is the probability that this crunchy caramel that I go out and I pick has a weight of less than 48 grams? So effectively what I'm asking here is what is the probability that x, which is the weight of our crunchy caramels, is less than 48, it's less than 48 grams, okay? Well, this is just a standard normal distribution question which we've done before in the last last video, okay? So we're basically saying here, well look, I need to standardize, I need to work out how far in terms of units of standard deviation is. 48 is away from 50. So how many units of standard deviation is 48 away from 50? And I do that through standardizing. So I simply just take this 48, I take away the sample mean, remember that shifts the entire distribution to the left, so it's centered around 0. And I also need to divide by my standard deviation because that effectively stretches it inwards, so I'm looking at units of standard deviation. So instead of looking at like every 3, which is what the value of the standard deviation is, I'm basically making it units of 1, which is like units of standard deviation. Now if I stick all that in my formula, my standardizing formula, I find that 48 lies 0.67 units of standard deviation below the mean. Okay, so because it's negative, it's below the mean. So in other words, 48 is 0.67 units of standard deviation below 50, okay, below the mean, right? So effectively what I'm looking for is what is the probability that I end up with a value which is less than negative 0.67 units of standard deviation, obviously below the mean, okay? Well, one way that I could write that, because I'm going to now look in my tables, I'm basically saying, well, okay, well, in my tables, I'm going to use phi for my symbol for looking up the tables, my standardized value, units of standard deviation value, whatever you want to call it, negative 0.67. What's the probability of obtaining a value which lies below 0.67 units of standard deviation below the mean? Well, in order to do that, just simply look it up in the tables, and I find myself 25.14%. So this is just really based on the example which I was doing in the last lecture, okay? But now let's suppose that I change the questions. And now let's bring in the central limit theorem. Let's suppose I change the question. Now let's suppose that instead of walking into the shop and choosing one crunchy caramel, which I was doing in the last question, let's suppose instead I choose 5 crunchy caramels at random. So instead of just picking up one, being a little bit more peckish, I pick up 5 crunchy caramels. I use some random sampling method to select them. What is the probability that this sample of crunchy caramels has a mean weight of less than 48 grams? Well, clearly now, my definition up here, my x is distributed normally using 50 and 3 squared. That was working with one crunchy caramel. Now I need to understand how this thing changes to deal with 5 crunchy caramels. Okay, so I'm effectively looking for, I know that the probability of getting one crunchy caramel with a weight of below 48 grams was 25%-ish, okay? Now just think, and I want you to kind of pause the video here, what should happen to this probability if I increase the sample size? So going from 1 crunchy caramel to 5 crunchy caramels, what should happen to this probability? Should it increase or should it decrease? Well, are you happy that we have just seen with this kind of normal distribution that as I increase the number of samples, my normal distribution becomes more peaked, which means that the probability of getting a value which is away from the true population mean, which is 50 in this case, so I know my true population mean is 50, the probability of obtaining a sample which is further away than 50 should decrease. Okay, that probability should decrease because effectively my curve is becoming more peaked. Okay, so I'm expecting this probability to decrease. But the question is, well, how? How do I change this distribution such that the probability will decrease? Well, let's just think. What I'm going to do is I'm going to look at each of my 5 crunchy caramels. So I go into my shop, I select my 5 crunchy caramels, and I'm going to look at the distribution for each of the crunchy caramels that I take in this sample. So I know that each crunchy caramel is effectively going to follow this normal distribution, okay? I define that in the question, okay? I know what the distribution is for 1 crunchy caramel. So in other words, each of these crunchy caramels, so crunchy caramel 1, which I'm going to call x1, is going to be distributed like this. Crunchy caramel 2, which I'm going to call x2, is distributed like this. So each crunchy caramel effectively follows its own normal distribution like so. So my question is, well, how do I combine this together to get a sample of 5 crunchy caramels? Well, are you happy that I'm effectively taking the mean weight of these 5 crunchy caramels? So I go through, I find the weight of each crunchy caramel, so x1, x2, x3, x4, x5, and I take the mean weight of all of them. So I'm basically just going to use the notation, well, capital X bar is going to be the mean weight of each of my crunchy caramels. Remember that each of my crunchy caramels, x1, x2, x3, etc., they're all going to be following their own normal distribution, which I've defined as such. So this is going to be the mean weight of all of my 5 crunchy caramels, x bar, okay? So I know that this kind of x bar is going to be following this kind of normal distribution. So in general, if I want to kind of generalize this, at the moment this is dealing with crunchy caramels, if I want to generalize this to n samples from a normal distribution, from any old normal distribution, it may not necessarily be 50 and 3 squared, any normal distribution that looks like this, I can basically say that it's going to be generalized like so, okay? But this is basically the specific case for my crunchy caramels. This is the general case, okay? Now, effectively what I'm asking here is what is the mean and what is the variance, okay? Because I want to know, well, okay, x bar, I know that that's still going to be normally distributed, right? I saw that with my curve, okay? I saw that with my curve here. I know that as I take more samples, it's still going to follow a normal distribution, okay? But my question is, well, okay, what's the mean and what's the variance? Because I know that if it's going to follow a normal distribution, so if x bar, the mean of my samples, is still going to follow a normal distribution, I effectively need to find out what goes here, so what's the expectation, and what's going to go here, which is the variance. Because remember, that's how I set up my normal distribution. Two parameters, expectation, or mean, and variance here. So I need to work out what is the expectation of the mean, so the expectation of x bar, and what's the variance of x bar, and then I'll have a new distribution for my mean of my samples. Okay, so let's do that. So let's just think. I've got all of my five crunchy caramels here, so I'm going to use this specific example. I've got my 5 crunchy caramels. They each follow a normal distribution, which I've defined generally as mu and sigma squared, okay? So we all know that they're going to be 50 and 3 squared, but I'm just going to do it generally, just for the sake of kind of generalizing it to other situations as well. So effectively, what I'm tasked with is finding what parameter goes here, so what the expectation is, and what the variance is, so what parameter goes here. Okay, so let's do that. So let's just think. I've just defined x bar as basically x1 plus x2 plus x3 plus x4 plus x5 all over 5. So more generally, it's just basically taking each individual random variable and dividing it by the number of random variables that you've got. That's how you take the mean that's how you take the mean, okay? And I'm asking, what is the expectation of x bar? So what's the expectation of this thing, okay? So, well, let's have a think. We can use our expectation algebra here. Are you happy that x bar is just basically all of these things? So I can rewrite that as each individual random variable, so each crunchy caramel, if you like, all divided by n. That's just basically using laws of fractions, okay? If I have loads of things added together in the numerator and I'm dividing them all by n, that's basically the same as taking each individual thing, dividing each individual thing by n, and then adding them all together. Okay, so let's have a look at this. So using expectation algebra, if I have the expectation of lots of individual random variables being added together, I know that, for example, expectation of 2 random variables added together will just be the expectation of each random variable added. Okay, so the expectation of x1 over n, I can write that as the expectation of 1 over x1, plus the expectation of 1 over x2. So basically all I'm doing is just taking the expectation of each of these individual terms inside my brackets. Now, are you happy that 1 over n, well, n is just the number of random variables. In this case, it's the number of crunchy caramels in my sample. So this is just a constant. And I know from expectation algebra that if I have the expectation of a constant times my random variable, that should be the constant times the expectation of my random variable. In other words, I can just pull my 1 over n out, okay? So I can basically just pull my 1 over n out like so. Okay, all right, so what can I do here? Well, I've basically got expectation of each of these things. I know that the expectation of each random variable is just mu. That's just whatever the mean value of each of these random variables are, okay? Because I know that x1 is normally distributed with mean mu and variance sigma squared. x2 is normally distributed with mean mu, variance sigma squared, etc, etc, etc. So the expectation of x1 should just be mu, expectation of x2 just mu, expectation of x3 just mu, etc, etc, etc. So effectively, I've got 1 over n times mu n times, haven't I? Because I've got n random variables there. So I can basically say, well, if I take n lots of those things, that should just be n lots of 1 over n times mu. Okay, that just makes sense because I've got n random variables. So I've got n lots of 1 over n mu. That's the expectation of x bar. Well, n times 1 over m, they cancel. So I'm just left with mu. So what I've basically shown to you there is that if I have a sample which are each made up of an individual random variable, so x1 is normally distributed with some mean and variance, x2 is normally distributed with some mean and variance, etc, etc. Remember, this corresponds to each individual crunchy caramel. Then I'm basically saying when I collect together that entire sample and take the mean weight of that entire sample, so the mean weight of all 5 of my crunchy caramels, which are each normally distributed, then I can say the expectation of that mean, expectation of that sample, should just be whatever the true population mean is. Okay? And that makes sense, okay? Because we said when we were looking at our curve here, that as we increase the number of samples, then we're basically approaching the true population mean. So in other words, if we look at more and more samples, the expectation of that sample should approach what the true population mean is. So in other words, it's just mu, okay? That shouldn't change. But my next question is, well, what's the variance? Well, I can employ a very, very similar technique with my expectation and variance algebra that I was doing on the last slide. So I know that x bar is just given by this. Okay, so I'm looking for the variance of x bar, the variance of my sample. So okay, let's just think about this. Again, I'm just going to write x1 over n, x2 over n. I'm basically going to distribute this divide by n over each of my individual random variables. And I can basically say, well, I'm looking at the variance of each individual random variable. So because I can understand that each of these things are independent of each other, so I'm assuming they're independent, each individual random variable, each individual crunchy caramel is independent of each other, then I can just say that's just the variance of each individual random variable. And then again, I can just use expectation algebra to say, well, okay, the variance of some constant times a random variable, okay, should just be that constant squared times the variance of that random variable. So here we go. So I've got 1 over n squared out the front of each of these things. Well, how many of those have I got? Well, I've got n times them, okay, so I've got n lots of them. So effectively, I'm just going to write the variance of each individual random variable as sigma squared, because I know that. Remember that the variance of my first crunchy caramel was just sigma squared, variance of my second crunchy caramel, sigma squared, etc. So effectively, I'm just writing the variance of each individual random variable as sigma squared. Now, how many of those have I got? Well, I've got n of them because I've got n crunchy caramels in my sample. So in other words, I can write this as n times each of these individual terms, so n times 1 over n squared times sigma squared. If I just do a little bit of simplification, I effectively get sigma squared over n as my variance of my sample. So there's the variance of my sample, the variance of my 5 crunchy caramels should just be whatever the variance is of 1 crunchy caramel, but then I'm decreasing it by a factor of n. Now, if you think about it, that should make sense, okay? Because we effectively said that the expectation of our sample should just remain the same, okay? That makes sense because if I'm looking at my curve, then the curve should remain centered around the same value. In other words, it should approach the true population mean. But I also said that with more and more samples, what's effectively happening is the spread of the distribution is decreasing. Well, okay, as I consider more and more samples, okay, so let me just show you that. As I consider more and more samples, the spread of my distribution is decreasing, it's becoming more peaked. Well, okay, if I just show you that then, are you happy that because I'm taking the old variance, so if I choose n randomly chosen samples from x is normally distributed with mu and sigma squared, then the variance should decrease by n? Because obviously as I increase n, I'm dividing by a bigger and bigger number. In other words, I'm taking sigma squared, which is constant, and I'm dividing it by a bigger and bigger number. I'm dividing it into more and more parts, which means that this thing here in my second parameter of my sample should decrease, which is exactly what I wanted. Okay, so those last 2 slides was kind of a proof of why that is true. But if you just want to walk away and just think that's all I need to know, so if I basically have a random variable like this, as I consider more and more things in my sample, then the distribution will actually approach this. This is how I combine all those samples together. Okay, so the mean should remain the same, but the variance should decrease by a factor of n. Now, it's really important to note that if I'm just looking at one random variable, then this thing here is called the variance, and obviously the square root of that is called the standard deviation. So standard deviation is given by sigma. Just remember, standard deviation is dealing with a sample. It's basically a measure of how far the things in your sample differ from the mean. What is the average spread from the mean, okay? But now what I'm doing is actually combining together lots of individual samples. So I looked at five things in my first sample, so 5 crunchy caramels. I could then do it again and look at another sample of 5 crunchy caramels, do it again, look at another sample of 5 crunchy caramels. So I'm effectively combining these all together. And as I'm combining them all together, I'm getting more and more things in my sample, which means that I'm approaching the true population. Okay, which means that I'm now talking about the standard deviation from multiple samples combined. So I no longer call this thing here, so this sigma squared over n, I no longer really call that the variance, because if I take the square root of that, that's no longer going to be called the standard deviation. So what I say is when I take the square root of my sigma squared over n, it's no longer the variance, or the standard deviation, it's going to be called the standard error. Because it's basically saying as you consider more and more things in your sample, you're getting closer and closer to what's actually happening at the true population level. So therefore, it's less of a measure of the standard deviation from the mean, the average spread from the mean. It's more a measure of, well, actually, how far out are you from where you're supposed to be? Because of course, if you're looking at the true population, you should expect to find a value close to the mean. So really now we call it standard error because it's measuring how far you are away from where you're supposed to be. Okay, so just a really subtle point, but actually really crucial. The standard deviation is basically just a measure of a sample. But because we're talking now about multiple samples combined with a central limit theorem, that's literally what that formula is telling you down there, then basically you wouldn't call this a sigma over root n. You wouldn't call this the standard deviation anymore. Okay, you'd call it the standard error instead, because it's measuring how far you are away from where you're supposed to be. It's what your error is. Okay, so it's called the standard error instead of standard deviation. Okay, good. So let's actually look back at our question. So my question said, if I walk into a shop and collect 5 crunchy caramels at random using some random sampling method, what is the probability that this sample of crunchy caramels has a mean weight of less than 48 grams? Well, okay, let's have a look at that then. So I've just said that the central limit theorem, if this thing up here, so the x is normally distributed with 50 and 3 squared, this is just for one crunchy caramel. So what I'm basically doing here is collecting 5 crunchy caramels. In other words, I'm taking a sample of 5 individual things. So I understand that this distribution should change. Well, how should it change? Well, first of all, x has to change to x bar because I'm taking the mean of my sample, so my 5 crunchy caramels, no longer just one crunchy caramel anymore, okay? The mean should stay the same, so in other words, whatever my mean was for my 1 crunchy caramel, it should remain the same for my mean of all of my crunchy caramels, so my samples combined. However, my variance should decrease by a factor of n. We've just seen that with the central limit theorem. So the spread of the distribution should decrease, and it always decreases by a factor of n. So 3 squared should become 3 squared over n. So therefore, if I just fill that in, I basically no longer need to consider this distribution up here. So the x is normally distributed with 50 and 3 squared. Because I'm looking at 5 crunchy caramels, then I can just consider this distribution on its own. So I know that the distribution for my sample is normally distributed with a mean weight of 50 and a variance of 3 squared over 5, because there's 5 things in my sample. And then effectively I'll just solve it in exactly the same way as before. So now I'm looking for the probability that the mean weight of my sample, so x bar, is less than 48 grams. That's what I'm after. So therefore I do exactly the same thing. So I standardize. So I use 48, which is the value that I'm interested in. I'm asking how many units of standard deviation does that allow from this distribution. So I need to take away the mean of this distribution, which is 50, and I need to divide by, remember it's not standard deviation anymore, it's standard error, but effectively just the square root of this 3 squared over 5. Well, of course, if I square root 3 squared over 5, well, square root of 3 squared is 3, square root of 5 is square root of 5, so it's going to be 3 over root 5. Stick that in a calculator. I basically understand that 48 will lie 1.49 units of standard deviation below this mean of this particular distribution, okay? So in other words, I just need to look up, well, what's the probability of obtaining a value less than 1.49 units of standard deviation below the mean? Look that up in the tables, and I find that's 6.81%. So let's just have a look at that then. Okay, let's just have a look at that. So I basically said that when I was just looking with one sample, so that was just simply the straightforward question that we did right at the very beginning with my crunchy caramels, I ended up with a probability that, so basically the probability of a weight less than 48 grams. So what's the probability in each case of obtaining a weight less than 48 grams? That's what I'm after. And I found that if I just went into the shop, picked up one crunchy caramel, the probability that that one particular crunchy caramel weighed less than 48 grams, I worked that out as 25.14%. Then I said, well, okay, as I increase the number of samples, so instead of just walking into the shop and picking up one crunchy caramel, instead I'm going to walk into the shop and pick up 5 crunchy caramels. Well, then what's the probability that the mean of that entire sample, all 5 of those crunchy caramels, what's the probability that the mean weight of those 5 crunchy caramels weighs less than 48 grams? I've just worked that out, is 6.81%. Now just think, does this satisfy the central limit theorem? Well, yes, I think it does. Because look, I'm basically saying that with one sample, the probability of obtaining something which is less than 48 grams is 25.14%. Then as I increase the number of samples, so in other words, as n approaches infinity, okay, I should end up with samples which are closer to what the true population mean weight is. Remember, the true population mean weight is 50 grams. So in other words, the probability of obtaining a sample which has a weight of 48 grams, which is away from the mean weight, the true mean weight of what it should be, the probability should dramatically decrease. It's the idea, if you take more and more samples, the idea is the probability of obtaining a sample which is further away from the true population mean, in other words, obtaining outliers in your data, should decrease. You're more likely to get values which are close to 50 and less likely to get values away from 50. And you can see that makes sense from what we've calculated, because as soon as I look at 5 samples, that probability dramatically decreases about 5 times less, to about 6 or 7%, okay? So just be aware of that. The central limit theorem is a really simple idea, and I cannot stress it enough. In fact, I can't stress it enough, so therefore I'm going to write it down again, okay, just to make sure it's really in your head. It's very intuitive. It's basically the idea that as you increase the number of samples, so as the sample size increases, and remember that we've said that the kind of key to collecting data, you want to collect as much data as possible. The more data you can collect, the better, because the more information you're getting about what's actually happening at the true population level. Okay? So as you increase the number of samples, it should be that whatever the sample mean weight is, that should approach what the true population mean weight is. So in other words, the measure which you're getting for the mean of your samples should approach what the true parameter of your mean is. Okay, so what the true mean parameter should be for the entire population. Okay, so that should make sense to you consider more and more samples. But it should also be the case that there's less deviation in your samples as well. Okay, so it should be that the majority of your samples should lie close to what the true population mean weight is. Okay, so in other words, if I just go out and collect one sample, I'll get a curve that looks something a little bit like this maybe. Okay, so that might be just one sample. There's a lot of kind of error in here. There's a high probability that you could get like outliers and stuff. But then as you consider more and more samples, that kind of error decreases. Okay, so in other words, you're more likely to get values in here than you are outside of that domain or outside that range. Okay, so that might be, for example, n equals 1,000. Okay, so it should be that the spread of your distribution decreases, and therefore by default, the probability of obtaining a value or obtaining a sample which is further away from that true population mean weight should decrease. Okay, so this is literally all the central limit theorem is saying. Okay, it's basically very, very logical. It's basically saying as you consider more and more things in your sample, it should be the case that your sample mean should approach what your true population mean should be, and it should also be the case that there's less spread in your distribution, which means that the probability of obtaining a sample which is an outlier should also decrease. And this kind of makes sense. It's very intuitive. So remember, all we're literally doing here is we're understanding, well, okay, if I have data about a sample, so if I have sample level of data, that means that I should still be able to infer what is happening at a population. Okay, so if I understand what's happening with a sample, the idea is because I understand what happens to my sample as I change sample sizes, okay, so the idea is you go out and collect as much data as possible, I'm able to infer then what's happening at population. So smaller samples should mean there's more spread in my data, okay, there's more probability of obtaining outliers and things, but then as I increase my sample sizes, it means that I'm getting closer to what should be happening at the true population level, okay. So if you want to understand how to infer samples from populations, you need to consider the sample size. And the idea is if you end up with a distribution like this, so let's suppose this is just one sample with some mean and some standard deviations. It's just like one sample here. Then as the sample size increases, then you can combine together multiple samples. This would be like n samples. So if you go out and collect one sample, you get a distribution like this. If you go out and collect more and more samples, then it should be when you combine those samples together, so x bar, you're finding the mean of all of those samples, it's still going to be normally distributed. That hasn't changed. However, the parameters will be slightly different. So first of all, whatever the mean of this particular one sample should be, it should approach what the true population mean is as well. So that should kind of stay the same. Okay, so the mean of the sample should approach what the true population is. However, the parameter for the variance should decrease by a factor of n as you consider more and more samples. That's basically saying that the spread of your distribution is decreasing. How does it decrease? It decreases by a factor of n. So the bigger the n is, the smaller the value of the variance. Okay, and that's just simple as that. It's just as simple as that. Okay, so let's quickly go through this example question together. So we're told that lifetimes of a particular type of battery are known to be normally distributed with a mean of 200 hours and a standard deviation of 3 hours. So in other words, you go out, you buy a battery, you expect it to last 200 hours, but there's going to be a little bit of deviation there, so the standard deviation is about 3 hours each side, okay? Now, find the probability that a randomly chosen sample of 50 batteries have a lifetime of between 199 hours and 202 hours, okay? So this kind of question here, perhaps you might want to go out and do a spot check, like a company that makes the batteries want to do a spot check to make sure they're sort of making batteries to the right quality and consistency. So they go out, they select 50 batteries at random, and they want to basically find the probability that they find these 50 batteries have a mean lifetime of somewhere between 199 and 202 hours, okay? So first things first, let's write down our normal distribution. So let X represent the lifetime of a battery, okay? And in this case, we need to write down the lifetime of just one battery. So I'm going to be using this first paragraph up here. So in other words, I'm saying that X is going to be distributed using a normal distribution. Well, what's the mean? Well, the mean is 200 hours. And the standard deviation is 3 hours, which means that the variance is 3 squared. So remember, it's always the variance that goes there. Okay. Then I'm basically going to select 50 batteries at random. Okay, so in other words, I go now and select 50 batteries. So this, remember, is just for one battery. It's the distribution for one individual single battery. Now I want to understand, well, what happens if I collect together a sample of 50 batteries? How does that change? How does my distribution change? Well, in this case, I want to work out the average lifetime of the batteries. So I'm going to write X bar. Okay, I know it's going to be normally distributed. Okay, the mean should remain the same as one battery, so the mean shouldn't change. Okay, it should just basically become more centered. So if the mean lifetime of one battery is 200 hours, the 50 batteries should still have an average lifetime of somewhere close to 200 hours as well. But the variance should dramatically decrease. Okay, remember that the variance decreases by a factor of n. So in this case, it decreases by a factor of 50. So I want to find the probability that the mean lifetime of these batteries, of this sample of 50 batteries, have a mean lifetime of somewhere between 199 and 202 hours. So I want to find the probability that the mean lifetime of my batteries, so X bar, is somewhere between 199 and 202 hours. Okay, so just remember that it doesn't matter whether I write less than or equal to, because it's a continuous random variable. So in this case, X less than or equal to and less than are seen as exactly the same things. So let's go about and do this. So first things first, I need to actually standardize this. So I'm going to be using this distribution here. I can forget about this distribution. This is for one battery. I've got my distribution for 50 batteries here. So let's actually go ahead and standardize each thing. So let's first of all standardize the 199. Let's find out how many units of standard deviation that is away from the mean. So I'm going to have Z is 199, take away my mean, which is going to be 200, divided by, well, I should say standard error in this case, but you can think of it as standard deviation. It's just the square root of my variance. So square root of 3 squared over 50 should just be 3 over root 50. Okay, that's my standard error there. Okay, so I'm just going to stick all of that into my calculator. So bring up my calculator, type my fraction button. I want 199, so I'll just scroll it over. I can't scroll it over. 199 minus 200, all divided by, now this is what I'm going to put in bracket, I want 3 divided by root of 50. Okay, so you don't technically need to put it in bracket, but I will just to be made sure. Hit equals, remember you want it as a decimal because that's the value you're going to look up in your tables. You get negative 2.36 there. So that's going to be negative 2.36 units of standard deviation below the mean, okay? So when I standardize this, I'm basically saying, okay, I'm looking for a value between negative 2.36 standard deviations of the mean. And I just need to find my upper unit of standard deviation. So I now need to standardize this thing. So that's going to be, 202 minus 200 divided by my standard error, which is 3 over root 50. Again, I'm going to stick all that in my calculator again, so clear that. Fraction 202 minus 200, which of course is 2. On denominator, again, bracket 3 divided by square root of 50. Oops, 50. Close the bracket, hit equals. Again, decimal I want. So that's going to be 4.714. 4.714. 0.14 units of standard deviation. I'll leave it to 2 decimal places because that's where my tables work. So in other words, my upper value of standard deviation, units of standard deviation, is 4.71. Okay, fine. So effectively, I'm going to try and look for this probability here. So the probability that I lie between 2.36 standard deviations below the mean and 4.71 units standard deviation above the mean. So I'm just going to make a quick sketch of my curve here. So here's my curve. Okay, I'm looking for an average value in the middle, so that's going to be 200. Sorry, that's going to be 0 because I'm working with my units of standard deviation graph now, so this thing here. Okay, and I'm looking for negative 2.36, and negative 2.36 is here. I'm looking for 4.71. Well, 4.71 is way out over here. It's well above the 3 units of standard deviation each side of the mean that we usually look at. And I'm going to basically be looking for what's the probability that I end up in that particular region. Well, are you happy that I'm going to basically look in the tables and look for all the values up to 4.71? So that's going to be the probability that z is less than or equal to 4.71, because remember my tables are cumulative. But then I'm going to have to take away the area which I don't want, which is the negative 2.36. So what's the probability that z is less than or equal to negative 2.36? Okay, so I'm going to look up both of these values. Now, are you happy if I bring up my tables now, that my tables only go 3.5 units of standard deviation each side of the mean? So actually, in this case, 4.71 units of standard deviation above the mean does not appear in my tables. But it's not an issue, because all that basically means that I've had nearly every single value that I expect up to 4.71. So basically like 3.5 units of standard deviation of the mean. If I look up 3.5, it's like basically 100%. Okay, it's basically 100% there. So 4.71, it's not quite 100%, so you've not quite had every single value, but it's pretty close that you can basically just consider it as 100%. So I'm basically just going to say, well, that thing there is near enough 100%, approximately 100%. So I should write this approximately. Okay, so it's approximately 100% because that value there is approximately 100%. Then I'm going to take away the probability that z is less than or equal to negative 2.36 units of standard deviation of the mean. So let's zoom in. Let's find the 2.36 or negative 2.36. So I'm looking at the negative 2.3 row, which will be that row there. I'm looking for negative 2.36, so I know that I'm going to be looking in this column here, okay? So if I just find the overlap between those two things, I find the overlap is 0.0091, okay? So 0.0091. So that's going to be 0.0091. That's going to effectively be, well, if I write that as 1 and I write that as 0.0091, then that means I don't have to convert fractions in my head while still remembering the number. In fact, it's 0.91%. So, okay, if I stick all that in my calculator then, so let's clear that. So we're going to have 1 minus 0.0091. Here it equals, and I find myself 99.09%. Okay, so 99.09%. So in other words, I'm basically almost certain, about 99% sure, that if I have these batteries, okay, so I know the distribution for the batteries, just like one battery, and if I put these 50 batteries together to form a sample, then I'm about 99% sure, so 99.09% sure, that I will end up that the sample of these batteries should be somewhere between 199 and 202, okay? So hopefully that makes sense, okay? Now what I'm going to do is I'm just going to give you your weekly task to have a go at. So I'll put it here on the screen. So it's going to be question 7, and these are found on the VLE if you want reference to them, okay? So it's going to be question 7. You've got heights of people in a college are known to be normally distributed with that mean height and that standard deviation. Groups are formed from random samples of students and the mean heights of these groups are recorded. So a group consisting of 1 student is formed. Can you sketch the probability density function? Then on the same graph, okay, a group consisting of 10 students are formed. Can you sketch the probability density function for this group? Same graph again, group consisting of 100 students is formed. Sketch the probability density function for this group. And then finally, can you just explain the relationship between your answers for part 1, 2 and 3? So can you have a go at question 7 for me for homework and upload that to Flipgrid for the weekly task, please?